Hello, my name is Maverick Madison, and this is Lab 1 for EEE120. Today, I'll be going over the half adder first. Half adders are used when we want to add two binary bits together. And as we can see in digital, we have input A and input B, and we have output sum and output carry. In order to get a value of 1 for the sum, whenever we're adding, only one of the inputs must be 1, while for carry, both inputs must be 1 to get a value of 1 for carry. To showcase this, let's simulate this circuit. So let's start it. As we can see, both A and B are off, or they're both 0. So our sum will be 0, and our carry will be 0. And if we were to turn one of the inputs on, let's say B, our sum will be 1, and our carry will be 0. And it will be the same if we invert A and B. A is 1, so our sum is 1, carry is 0. And let's try setting both of our inputs equal to 1. As we can see, sum is now 0, and carry is 1. Why have all these happened? So whenever we had both of our inputs off, we have no inputs going into the XOR gate, and the XOR gate needs only one of the inputs to be 1 in order to have our sum being 1. And for our AND gate, we need both of the inputs to be 1 in order to have a carry of 1. So this is why whenever we had one of the inputs on, we had a sum being 1 since one of the inputs was 1, but our carry is 0 because only one of the inputs is 1. And as we saw for when both the inputs were on, or 1, our sum was 0 because we only need one of the inputs to be on to have a sum of 1. However, for carry, since both the inputs are 1, we have a carry of 1. Makes sense whenever we're adding two binary bits. Now that we see that this logic matches, let's go into GTK wave to see another representation of this. So as we can see in GTK wave, with A being 0, B being 0, we have a carry of 0 and a sum of 0, similar to what we saw in digital. With B being 1, A being 0, we have a sum of 1 and a carry of 0. Makes sense? A being 1, B being 0, we have a sum of 1 and a carry of 0. Again, one of the inputs is on, or 1, so we have a sum of 1. And when both A and B are 1, we have a carry of 1 and a sum of 0. So again, when both the inputs are 1, we will have a carry of 1, but a sum of 0. We use the incrementer when we want to increment our chosen 4-bit number by a numerical value of 1. So in the schematic, we take an input decimal number and convert it into a 4-bit binary representation via a splitter/merger, which is this long black line right here. Each of the bits of the converted inputted number is the input for the A value, which goes into each of the half adders as shown on the screen in digital. And we recently discussed half adders, so we know what those are. Our other input is inc, which acts as the input value B going into the half adders above. This input will pretty much act as a +1 to our input for A, which gives it the name inc for incrementer. Again, if both A and B are 1, then we should expect a carry, which acts as the input to the next input B for the half adder above each one. However, if only one of A or B is 1, then we should have a sum which leads into another splitter/merger, as shown here, of 4 bits to represent the desired number in the binary. But instead of decimal to binary, we're doing binary to decimal to eventually get our final value y as our output. Also, we should always expect carry as our output to be 0, unless we do one thing, and that is set our A input to be 15 and our incrementer to be 1. And this is because 4-bit binary numbers only go from 0 to 15. So the value 16, 15 plus 1 would indicate a value of 1 for carry. And essentially, the sums would all not exist as 1, but 0. Since 1, 1, 1, 1 would indicate 15, and 16 would be 1, 0, 0, 0, 0. And the 1 would essentially be the carry. So now let's just run a little example in digital. So say if I were to choose a number like 6, let's do 6. Okay. Without even turning the incrementer on, we have our output being 6. This is just how it works. We have not incremented anything, so we will have a binary value of 6 at the end. But if we turn the incrementer on, we will get our incremented value by 1, which is 7. So this is literally just adding 1 to our binary value, and it's going to change from binary back to decimal, which is plus 1 of our input A. Now let me change our example to 15 now. And let's turn the incrementer off before we do that. So we have the value 15, which is F in hexa. So we have our output Y being 15, or F, without even turning the incrementer on. But when we turn the incrementer on, we will see that the carry will then be 1, and this will be 0 as our Y. And yeah, so carry would be 1, and our output Y would be 0, as I said before. We cannot represent 16 in 4 bits. It's 5 bits for 16, so that is basically why that happens. So as we can see for this, whenever our A input is 0, decimal value 0, and we increment it by 1, we will get our value Y being 1. And this is the same for every single decimal number all the way up until 14, with the incrementer being 1. So 0 will go 1, 1 will go 2, 2 will go 3, 3 will go 4, etc., etc. But whenever we set the A value to be 15 and our incrementer is 1, we will have that carry value, and our Y will be 0 while our carry will be 1. And then these are some other examples. If the incrementer is off, we have our value of 0, 1, 2, and it'll just be the same for our Y value. Now we move on to the full adder. This is used when we want to add 3 binary bits together. As we can see, we have input A, B, and carry in, with outputs being sum and carry out. To get to our sum, we need to use the same logic for XOR as before. However, using 3 inputs, the sum will be 1 when an odd number of inputs are 1. So that would be 1 or all. So one of the inputs being on, or all 3 of them being on. For carry out, we derived a formula in class to showcase carry out through the truth table for addition, which is represented as just carry out is equal to A carry in plus B carry in plus AB. In that case, we have our 3 AND gates shown right here in digital, and our OR gate to get our value for carry out. Now let's move on to some examples. Using this example with A being 0, B being 0, carry in being 0, we have our sum being 0 and our carry out being 0. Why is this? So the XOR gate needs 1 or 3 of the inputs to be 1 in order to get a sum of 1. And in this case, none of them are 1, so we have a sum of 0. And for our carry out, we need 2 or 3 of the inputs to be 1 in order to have a carry out of 1. And in that case, none of the AND gates have a full output of 1 since all of the inputs are 0. So we have a carry out of 0. Now let's just do another example. Let's just turn A to be 1 and keep all the other inputs as 0. Now sum is 1 and carry out is still 0. Why is this? The XOR gate now has one input being 1 going in, and therefore we can see that our sum is 1. In order for the XOR gate to have an output of 1, 1 or 3 of the inputs need to be 1 in order to have our sum being 1, which is the case. However, for carry out, we can see that with A being 1, it leads into this top and this bottom AND gate. But with B being 0 and C in, or carry in being 0, none of the inputs can be met for an output of 1. So in this case, carry out is still 0. Now let's turn the inputs on. Let's just turn carry it on now. Now we can see that sum is 0 and carry out is 1. Our XOR gate has an even number of inputs being 1, so our sum is 0. And for our carry out, we can see that with A being 1 and C in being 1, we have the 2 input wires leading into this top AND gate, which gives us an output of 1. And since it leads into an OR gate, only a minimum of 1 of the inputs for an OR gate needs to be 1 in order to get an output of 1. So we have a carry out of 1. And if we turn all inputs on for our last example, we can see that sum is 1 and carry out is 1. This is because XOR sees 3 inputs being 1 in order to get a sum of 1. And carry out sees all of our AND gates wires of the inputs being fulfilled. So we get outputs of 1 for each of the AND gates. And for our OR gate, we have all the inputs being 1, so we have a carry out of 1. So as we can see with A being 0, B being 0, carry in being 0, again, we have carry out being 0 and sum being 0. with just one of the inputs being 1, with CN being 1, B being 1, and A being 1. So for this wave, this wave, this wave, we have carryouts of 0, but sums of 1. Since that's our XOR gate, we only need one of the inputs or 3 of the inputs to be 1 in order to have an output of 1 for sum. Now with B and C in being 1, so an even number, we have a carryout of 1, since that fulfills one of the AND gates to have an output of 1. But our sum is 0 since it's an even number going into the XOR. Finally, we have our 4-bit full adder. We use this when we would like to simulate 3-input 4-bit addition with 2 decimal numbers. As you can see, we have input A, B, and carry in with outputs carry out, overflow, and Y, which signifies our final number after adding everything. Our inputs A and B signify the 2 decimal numbers we would like to add before again turning them into 4-bit binary numbers using splitters and mergers for both A and B. The bits of each lead into the corresponding input for A and B for the full adder as described before. So A, B, A, B, A, B, etc. In this situation, we are also using carry in as an input here. So if you would like to have carry in, it would lead into the first full adder's C in input. Using the gate logic as before, in the full adder circuit, an XOR needs an odd number of inputs to be 1 in order to generate a sum of 1, while carry out needs 2 or more inputs to be 1 in order for the carry out to be 1. I must add that if carry out is in fact 1, the value leads into the following carry in input for the next full adder, while the sums familiarly just lead into the corresponding bit in another inverted splitter/merger. There are a few things, however, for the schematic that are a bit different. For the final carryout to be 1, as per simple 4-bit addition, the final carryout simply must be 1. For overflow to occur, the second to last carryout, or the last carry in, and the final carryout must not match. In other words, one must be 1 and the other must be 0 in order for there to be overflow. Now I'm going to show examples in Notepad as according to my test cases to clearly show that these outputs are true in action before heading into GTK Wave to finish up this lab. So these are my test cases for this lab. I decided to carefully choose each one of them in order to test them in digital itself. In this case, I'll just select a few of them and add them all up in Notepad just to show you what we should expect in the 4-bit addition whenever we do it in digital. So here are all my examples written out in Notepad. So first, let's go over the first one. We have A being 3, B being 2, we have a carry-in of 1, and we have an expected sum of 6, and no overflow and no carry-out. So let's test that. So let's do A being 3, B being 2, carry-in being 1. Simulation. Start. So 3, 2, and 1. So we have no carry-out, no overflow, and an expected sum of 6. So that was correct. Now let's move on to the second one. A being 9, B being 6, carry-in being 1, expected sum being 0, and we have a carry-out of 1. So let's simulate this again. Yep, 9, 6, carry in. So we have a carry out of 1, overflow of 0, and we have an expected sum of 0, which is correct. Here we have our next example. We have our A value being 8, our B value being 14, we have a carry in of 1, expected sum of 7, and then we have overflow and we have a carry out being 1. So we have a value of 3 there. So let's go and test that out. So we have 8, we have 14, and we have a carry in. So here we have our expected sum of 7. We have a carry out of 1 and an overflow of 1, which is correct. And for our last example, we have A being 7, B being 3, carry in with 1, our expected sum of 11, and we have overflow, but no carry out. So let's test it out. We have A value of 7, B value of 3, carry in of 1. 7, 3, carry in of 1. We have no carry out, we have overflow, and we have an expected sum of 11. So that was also right. So those were all of my examples from the selection of my test cases that I made for the 4-bit adder in digital. So finally, let's just move on to GTK Wave to show you guys the final waveform of this schematic. So here's the final waveform for the 4-bit full adder. So from my worked out examples in Notepad, here we can see a similar representation in the waveform. So here in this first example, we have A being 3, B being 2, carry in 1, expected sum of 6, and no overflow or carry out. So here we have our A value being 3, B value being 2, carry in of 1, expected sum of 6, and then no carry out, no overflow. So let's move on to the second example. We have our A value being 9, B value being 6, carry in being 1, expected sum 0, and we have carry out, but no overflow. So we can see that in this waveform right here, A value of 9, B value of 6, carry in of 1, expected sum of 0, carry out of 1, no overflow. Correct. On the third example, we have A value of 8, B value of 14, carry in of 1, expected sum 7, and we have overflow and we have carry out. So let's find that. A being 8, B being E, or 14, carry in being 1, expected sum 7, and we have carry out and we have overflow. So that was correct. And for the last example we went through, A value of 7, B value of 3, carry in of 1, expected sum of 11, and we have a overflow but no carry out. So 7 and 3, A value of 7, B value of 3, carry in of 1, expected sum of 11, no carry out, overflow. Nice. Waveform works accordingly, and this works for all of my other test cases. All of them passed. So yeah, that was lab 1. My name is Maverick Madison, and this was for EEE 120.